Hi, in this session, we discuss ABL tree. What is ABL tree? ABL tree is a self-balancing binary search tree or height-balanced binary search tree. ABL tree is also a binary search tree, but it is a balanced binary search tree. Why we go? What is the need of ABL tree? We have a binary search tree. Then what is the need of ABL tree? We know tree is a data structure, and we can perform operations like search, insertion, deletion, delete a node from the tree structure, and it is a nonlinear data structure. And the time complexity of the tree is less compared to array and linked list, which has order of log n time. So consider why ABL tree. What is the need of ABL tree? Means see this diagram. Here, this is the balanced binary search tree. The balanced binary search tree means here the height of the left subtree and height of the right subtree are equal. Okay, this is a balanced binary search tree. So if you have balanced binary search tree, its time complexity is order of log n for all operations, search operations, then insertion operations and deletion operations. We have order of log n time if it is a balanced binary search tree. And if it is an imbalanced binary search tree, not a balanced one, either a left skipped binary search tree or a right skipped binary search tree, then for a search operations and deletion operations, it requires order of n time. So what we can say, the time complexity is purely on its height of the binary search tree. If height is equal to n and it's a maximum height is n, then its time complexity is order of n for the first case. So its time complexity is purely based on its height. If it is a left skipped or a right skipped binary search tree, then its time complexity is order of n for searching and deletion operations. If it is a balanced binary search tree, then we have a order of log n time which is lesser than that, because order of log n is less than order of n time. So for that, we make all tree as a balanced one, we need ABL tree. To make all binary search tree as a balanced one, we need ABL tree. How the name comes ABL is, it is named by Adelson, Wilsky, and Landis. This is the inventor who invents this ABL tree. Adelson, Wilsky, Landis is the author, which means inventor. Their first letter we call this is the AVL tree. And the AVL, as I said before, AVL tree is a self-balancing or height-balanced binary search tree. So to do balancing, to make in AVL tree, we make all binary search tree as a balanced one. So what is balancing? What it requires? So to make the tree as a balanced one, we need two terms. The term is height and balancing factor. Two term is height and balancing factor. So the balancing factor of each node in the ABL tree is either 0, 1 or minus 1. None other value not allowed. That is, it may be a minus 2 or 2 or not allowed. Only the value of each node is either 0, 1 or minus 1. If the node has either 0, 1 or minus 1, then that tree is a balanced one. Balanced ABL tree. It's a balanced binary search tree. It's called a ABL tree. If it is not, if any node has this value, then it is not a ABL tree, which means it may be 2 or minus 2, then it is not a ABL tree. We have to make it as a balanced one. To, to make it as balanced one, and we call this as a ABL tree. So, as I said before, balancing factor, how to find balancing factor? Balancing factor height are important term here, factor here. How to find balance factor? How to calculate balance factor? Balance factor of any node is height of the left subtree minus height of the right subtree. What is height of the left subtree and height of the minus subtree is a balance factor. And once it is balanced, then we call this as ABL tree. And since it is a balanced one, its time complexity is order of log n. So ABL tree time complexity is order of log n. I said before, height and balance factor are important term. What is height? Height is the longest path from the root node to the leaf. That is height. Height, you want to find the height of any node, then height of that node to the its leaf node, maximum height. That is longest path. It's a height. What is balance factor? Balance factor is height of the left subtree minus height of the right subtree. This is one example of finding balance factor. After this, we will discuss how to construct ABL tree. So the balance factor is represented by F. BF equal to HL minus HR, which means height of left subtree minus height of right subtree. It's absolute one. It's height of left subtree minus height of right subtree. Now consider this tree structure. We find balance factor. The 0, 1, minus 1 are all balance factor. We find balance factor for each nodes and check whether it's a ABL tree or not. So first find balance factor of this root node. What is the balance factor of this root node is BF equal to height of the left subtree minus height of the right subtree. What is height of the left subtree? Maximum height. Longest height means longest path from root to the leaf because it's root. 1, 2, 3. Path. This path we have to consider. 1, 1, 2, 3. This is the maximum height. 1, 2. We have another path also that is 1, 2. So this is so longest maximum path. We have to take the longest path. So that is 3 minus this left is longest left height and what is the right height of the right subtree? Longest path. It has three path 1, 2, 3 and 1, 2, 3 as well as 1, 2, 3. Three paths it has. All paths are equal height only, so it's a 3 1. So 3 minus 3 equal to 0. So balance factor of 25 is 0. Then what is the balance factor of 20? So balance factor of 20 is height of the left subtree minus height of its right subtree. Sorry, height of its right subtree. Height of the left subtree is 2, 1, 2. So 2 minus height of the right subtree is 1. 2 minus 1 is equal to 1. Balance factor. What is this 10? 10. 10 is it has no leaf left subtree, left node, only right node. So height of the left is 0 minus height of the right is 1. One path is there. So it's minus 1. So minus 1 is balance factor of 10. Then what is the height of this balance factor of 22? There is no left child, right child. There is no leaf means that is 0. 0 minus 0. 0. 0, 0, 0, 0. Here, the height of the left subtree is 1 and height of the right side is 0. So 1 is the balance factor. So this is how we have to find the balance factor for each node in the ABL tree, binary search tree. This tree we call it as a ABL tree because each node has a balance factor of either 0, 1 or minus 1. So this is the ABL tree. Now let us discuss how to construct ABL tree. Before construct ABL tree, we should know one terminology, that is how to find the maximum possible number of nodes in ABL tree. The maximum possible number of nodes in ABL tree is, this is the formula, 2 power h plus 1 minus 1. What is h? H is a height. What is the height of this tree? Is a 3 is the height of the tree. So 2 power 3 plus 1 minus 1 is equal to 50. Total number of nodes in the maximum possible number of nodes in this ABL tree is 50. So this we should know when we how many number of nodes present in ABL tree. The question arises. Then this is the formula, 2 power h plus 1 minus 1. Now we construct ABL tree. For this, we have four cases. For constructing ABL tree, we have to consider four cases. What are the cases here? To make the binary search as a balanced one, we do some operations. What operations? Rotation operation. Rotation. It needs rotation. So what rotation it requires? How to make it as a balanced one? For that, it has a three cases. When it requires a rotation, that cases when it requires rotation means if it is a left imbalance, if it is right imbalance case, if it is left imbalance case, or if it is right imbalance case, it requires a rotation. If it is left imbalance case means it requires a right rotation, only single rotations. Both the left imbalance case and right imbalance case requires only single rotations. So what is the left imbalance? Left imbalance means the node is, your tree structure is like this, means this is left imbalance. So it requires only single rotations, right rotation. So you get like this, right rotations. If it is right imbalance, see here, if it is right imbalance, then it requires left rotation. Suppose your tree structure is like this, then it requires a single rotation, that is left rotation. Single rotation, left rotation. So the node will come here. So this will come here. This A, for example, this is 3, 4, 5. Means 4 will go here, then 3, then 5 here. Single rotation. So you have to we have to pull this 3 down, 4 will go. This is a single left rotation. If it is left-left imbalance, left-right imbalance, then it triggers left-right rotation. Suppose left-right imbalance means your tree structure is like this. It is left-right imbalance. Then what we have to do? We triggers two rotation, that is double rotation, but this left right, no, left right rotation itself, rotation also left right rotation. First we have to do left rotation this side, this one, the lower level, then we have to do upper level. So if you do lower level, then for example this is small a, we have to say that is it's a 10, it's, 8 9. Okay, so what you have to do, you have to rotate it this one, 9 will go here, 8 will come down, then 10. Again, right rotation in this level, right rotation in this level. So if you do right rotation 9, 8, 10. So this is left rotation. That is left rotation in lower level, then right rotation in upper level. Right rotation in upper level. Then right left imbalance case. If your tree is structure is like this, right left. So right left means rotation also right left, rotation also right and left. So where we have to do first right rotation is lower level. First we have to rotate it lower level, then we have to rotate it in upper level, right rotation, because it's a left tree. So right rotation requires. See, if it is like this, tree structure is like this, a right left hand side, then rotation also right rotation, then left rotation. First right rotation in this side, this part, then left rotations. So this is the case. So if you want to insert any node at the time, if this case is like this, either left left imbalance or right imbalance or left right or right left imbalance, the tree means, then we have to rotate it. If it is left left imbalance case, it requires only right rotation, that is single rotation. It is right imbalance, it requires single rotation only, but it is left rotation. Because this is a LL imbalance, RR imbalance, LR imbalance, RL imbalance. If it is LR and RL, rotation also left right rotation, right left rotation, but from lower level to upper level. This is a diagram for that. If the cases is left left imbalance, right imbalance, what is the solution? Solution is rotation. Solution is rotation. What rotation? Either single rotation or double rotation. That is the matter. It occurs if it is a left left imbalance and right imbalance means single rotation. But if a left imbalance means right, we have to do right rotation. In somewhere they will tell is as a LL rotation and this is a aura rotation, but we need not to get confused by seeing those things. Just if it is left left imbalance means we have to do only single rotation as a right rotation. If it is right imbalance means we have to do only a left rotation as a single rotation. If it is double rotation means LR rotation, rotation also left right. If it is RR RL imbalance is case is imbalance, then rotation also right left rotation, but it's a double rotation. First, when you rotate, we have to rotate lower side, then upper side. Let us discuss the example. The first one, left imbalance case. Left imbalance means we need a right rotation. So, if you want to insert element 3 to 1, so how to insert a 3 to 1? 3 is first element, then again next element is 2, which is less than 2. So we have to go to the, we have to, while constructing ABL tree, we have to check the binary search tree properties. What is binary search tree property? Always we know the binary search tree property. Always the left child is less than a root, left child is less than the root, and this is a root node. K is a root node means K is a root and its left child is less than, left side is less than root, less than K, and its right side is, right child is greater than right, or right subtree node is greater than K. This we know. This is the property for the binary search tree. What is the property of binary search tree is the left subtree is less than the root and right subtree nodes are greater than the root. Left subtree nodes are less than the root and right subtree nodes are greater than the root. This is the property of the binary search tree, because ABL tree is also a binary search tree. While constructing, we have to follow the BST rule. So 3 is a, since tree is empty, we have inserted 3 as a root node. Then next element is 2, inserted 2 as a compare 2 with the 3 which is lesser, so it has to go to its left hand side 2. Then again the next node is 1. One is, next element is 1. 1 is compared with the 3 which is lesser, again you have to go to its left hand side, again one more node is there, that is 2, which is 1 is lesser than 2, again you have to do it, place it here because there is no node here, you have to place this is the place for 1. Now the tree is, we have to check the balance factor. What is the balance factor of 1? 0, because there is no left child, it's a 0. What is the balance factor of this 2? Balance factor of 2 is 1 minus 0, so 1. What is the balance factor of 3? 3 is 1, 2. 2 minus, there is no right child, 0. 2 minus 2 is equal to 2. So its balance factor is 2. So this is not, because we know that ABL tree has only either minus 1, 0 or 1. But here is 2. So it is not a balanced one. We make it as a balanced one. Further, we need rotation. So, but what type of imbalance is this? This is left-left imbalance. So we have, it requires right rotation, single rotation, right rotation, single rotations. So after rotate it, 3 should come. You have to pull 3 this side and 2. So right rotation. So you can, since it's left, LL means it requires right rotation. It's left skewed binary search tree. So 2 will go here, 3 and 1. Now check the property also. Property, what is BST property? BST property is left child is less than the root and right child is greater than the root. So now BF of this is 0, BF of this is 0 and this is 0. So this is a balanced one. Next one. Right. Example for right imbalance case. If it is right node means it requires left rotation. What is single left? That is single rotation. So what is a example data given is 1, 2, 3. Construct here a tree is a 1, and next one is 1. Since tree is null, we have to insert this as a root node. Then 2 is greater than 1, so insert here as a, its right hand side. And 3 is compared with 1 which is greater, and 3 is compared with the 2 which is greater, so it has to go to its right hand side, right child as a right child. Now check the BF. BF of this is 0 and BF of this is minus 1 because there is no child. So 0 minus 1 is minus 1. Here 0 minus 2 is minus 2. Here 0, there is no left child. And minus the two children, the height of this tree. The no right child means there is no height here. And the height of this right hand side is minus 2. So BF is minus 2. BF is minus 2 here. So what is this? This is a minus 1, okay, and 0, okay, but this is minus 2. Minus 2 means it is not a ABL tree value, BF value. So what we have to do? We have to do the rotation. Since it is a right skewed node, right imbalance, it requires left single rotation. So when you rotate it, 2 will go here and 1. We have to pull down 1 and 2 up. So 1, 2, 3. So now check BF of this, all this thing is 0, 0, 0 because height of the left subtree is 1 and height of the right subtree is 1 is 0 minus height of the left subtree minus height of 0. Now it's a balanced one. Now let us discuss for left right imbalance case. So consider this number 3, 1, 2. Construct 3 is a root node because it's first node, and next element is 1. 1 is less than 3, so it has to go to its left hand side. Again 2 is compared with the 3 which is lesser. Again 2 is it has to go to its left hand side, and again there is a node 1, and again 2 is compared with 1 which is greater, so it has to go to its right hand side, that is 1 right hand side, right check. Now check the balance factor. What is the balance factor of this one? Is 0 because no child. What is the balance factor of this one? Balance factor of this node is there is no height here because there no child, there is no height. 0 minus 1 because 1 height is 1 here, so 0 minus 1 is 1 balance factor. What is the balance factor of this 3? Balance factor of 3 is here. What is the height? 1, 2. The path, the longest path, 1, 2. So 2 minus here right hand side there is no child, so no height, 0. So its value is 2 here. So if it is 2, then it's not a EBF value. It's not a ABL balancing factor balancing factor. So what you have to do? We have to, it's an imbalanced tree, so we have to make it as a balanced one. To further, what rotation it requires? Since it is a left to right, see here we have to check its left to right, and rotation also can be done for the 3 nodes. Only 3 nodes it requires rotation, and left to right, since this node is the only three elements. It requires a simple height only, that is only two steps of level. So left, right. So L and R. If it is LR, rotation also left, right. But we have to do first lower level, then we have to do upper level. First do right rotation this level, then right left rotation this level, upper level. So if you do right rotation this level, two will go here. So two will go and one see the right rotation two, this two will go here, this one, sorry, this one, left right rotations, left three, one, and we have here two here. So two means left right. It is left right rotation also left right. But while rotated, first you do left rotation in the lower side. Rotations also requires right rotation. But first left rotations in lower level. Lower level means this leaf level. Then this is so you have to rotate it. So two will come here, one will go here. Two, one, and three. Then again right rotation. Now it requires right rotations. Lower level. Now it's upper level rotations. The upper level rotations. Lower level rotations left and upper level rotations is right. So here LR. So if imbalance is left right imbalance case, for left right imbalance case, rotation also left right. But in the first you do lower level, then upper level, lower level, then upper level. So double rotation, it requires double rotation. So what happened? Two, if you rotate here, this right hand side, then three will come here, two as a root and one. So this is the case, this is the diagram. So here if you check the balance factor, all will come 0, 0, 0. So it's guilty. Now take right left rotations. In the right left rotations, in balance case, first we have to insert 1 here, then 3 is greater than 1, it has to go to its right hand side. Again 2 is compared to 1 which is greater, again 2 is compared with 3 which is lesser. So it has to go to its left hand side of left hand side of 3. So that is 2. Now balance factor of this is 0, and balance factor of this one is 1 minus 0 is 1, and balance factor of this was 0 minus 2, 0 minus 2. The height of the left subtree is 0, height of the right subtree is 2, so 0 minus 2 is 2, minus 2. So balance factor is minus 2, so it is not a ABL tree. So we have to make it as a balanced one. So for that we have to find out what rotation it is. What rotation is? This side is right left, right hand side left. This is present in right hand side left. So right left means rotation also right left. First we have to, where we have to do rotation, this level. First we have to do lower level of right rotation, then upper level of left rotation. The lower level of right rotation, then upper level of left rotation. If we do so, so what we have to get? 1, rotate 2 and 3. 2 will go here, first lower level, 2 will go here and 3 will come. Then what we have to do? We have to do left rotations. Left rotation 1, 2, 3. So if it is a right left imbalance case, rotation also right left. For that we have to do its lower level first, then upper level. Right rotation, then left rotation. Now, what are the operations can be performed in the ABI search operation, insertion, deletions? So to insert element, before going to insert any element in the binary ABL tree, we have to consider its balance factor. So once you insert any node in the tree, we have to consider. See, operations on any tree is search, insertion, deletions. First, we discuss insertion, which means we are going to construct an ABL tree. Here we discuss example how to do the rotations, left rotation, right rotation, left rotation, left right rotation, right. And this right rotation also called right rotation or a rotation. Left rotation is also called left LL rotations. But the thing is, if it is right imbalance means left rotation we have to do. So both left and right are single rotation, and left right and right left are require double rotations. While rotating double rotation, first we have to do in lower level, then upper level. So the operations we are going to do is insertion. Insertion means we are going to construct one ABL tree. That how to construct that ABL tree is, uh, insertion, it requires insertion only. To construct any tree, it requires insertion. So we will see insertions. While constructing ABL tree, we have to do the rotation then and there. Don't construct the entire tree, then we go for the rotations. So we can do so, but if you do immediately the rotations, then we'll get a proper ABL tree within a less time. So first, for insertion operations, this is the algorithm. And after inserting each element, we have to check its balance factor. If the balance factor of every node is 0, 1, -1, then we move to the go for next insertion. Otherwise, we have to rotate it and make it as a balanced one. First, construct a wheel tree by inserting an element 1, 2, 3, 3, 4, 5, 6, 7, 8. Now we are going to insert 1 to 8 element. First, the node value is 1. To insert 1, since T is a null, we have inserted 1. Then what is the next value? 2. Inserted 1 and it's also balanced. T is balanced. Next is 2. Now we have to insert a 2. For that, we have to compare 2 with 1. 2 is greater than 1, so it has to go to its right hand side. Okay, what is the balance factor of this 2? Balance factor of this 2 is 0 because there is no right node. So right child height is 0. Balance factor of this is 0 minus 1 is -1 now. Done. So this is 10. What is the next value? 3. Now we are going to insert a 3. So 1 already there, 2, and its balance factor is -1, 0. 3. 3 is compared with the 1, which is greater. Again, 3 is compared with the 2. It has to go to its right hand side. 3 is compared with the 2, which is greater. So it has to go to its right hand side, 3. So now balance. What is the balance factor of this one? The balance factor of this is now it's a 0 because there is no left and right. Balance factor of this one is a 0 minus 1 is -1. And the balance factor of this one is a 0. There is no left hand side sub 3. So height is 0 and right hand side is 2. So -2 equal to -2. So now the balance factor of this one is -2. BF. What is the balance factor? Balance factor equal to -2. So now it is a, what is that? LL, because not LL. This is right hand side, right cubed balance tree. Right hand side. It's a right cubed binary search tree. If it is a right, this is right. Okay, this is right. Then what we have to do? We have to do left rotations. To make it as a balanced one, we have to do left rotation. If we do left rotations, what happens? Only single rotation is enough, left rotation. If it is right skewed, we have to do left rotation. Right imbalance means we have to do this for case number 2. Right imbalance. So left rotation, 2 will go here, 1, 3. Now check the balance factor. It is 0 and this is 0. Balance factor of this is 0. 1 minus 1 is 0. This one. Now the tree is balanced. After that, tree is balanced 1. Now left rotation it requires. So after done left rotation, now tree is balanced 1. Next one. What is the node? Insert. We are going to insert 4 here. So we have inserted 2, 1, 3. Now we are going to insert 4. For where 4 should come? 4 is greater than 2, which it has to go to its right hand side, and 4 is greater than 3, it has to go to its right hand side. 4. Now what is the balance factor? Balance factor, now we have to find balance factor of this one is 0 because 0, 0, height is 0, and balance factor of this one is 1 minus 0, so it's 1. Now balance factor here. What is the balance factor of this node? 1 minus 2. 1 minus 2 is, see here, 1 minus 2 is equal to -1, is -1. So the balance factor of this is -1. This is 0, 1. So all BF is here. This is 2. It has root node has -1 as BF, and this node is 1 as BF, 0, 0. So it's a balanced one. So no rotations required. So here, since this after inserting 4, everything the balance factor must be changed. After changing the balance factor, it is a now ABL tree. There is no need of rotations. Okay, now afterwards. Now we insert 5. Where to insert 5? We have to insert 5 here. So then we have to insert 5. 1, 3, 4, 5. 5 is greater than 2, which has to go to its right hand side. Greater than 3, go to its right hand side, greater than 4, go to its right hand side, 5. Now what again we have to check its bf. This bf is 0, this bf is 0 minus 1 is minus 1, this bf is what is bf here, 0 minus 2, 0 minus 2 is minus 2, here is bf is what is it, 1 minus 1 2 3, 1 minus 3 equal to minus 2, this bf is 0. So here also its bf is not allowed, minus 2 is also not allowed here, by balance factor minus 2 is not allowed. What we have to do, we have to do rotations. What rotation that we have to find, what imbalance is this, what type of imbalance case this is, right imbalance, because the all this in right hand side, right imbalance. And one more thing, how to find this right imbalances, we have to check this right. So we have to take the first two step, right, this right hand side we have inserted, so take right. Now this is also minus 2, this is also minus 2. Where to rotate, which whether we have to rotate at this one or at this one, whether we have to rotate at this three nodes or these three nodes. We have to rotate lower only. First we have to give preference to lower level only. We have to rotate at this one, these three nodes. Then we have to check the bf, whether it bf is 0 1 or minus 1. Now since it is in right imbalance, it requires only single left rotation. Right is, right imbalance, single left rotation. So if we rotate this one, what happened, 3 will go here, 4 will go here. So if we rotate 1, 4 will go here, 3 and 5. Now check its balance factor. Balance factor of this 5 is 0. This is 0. This one is 0. Because 1 minus 1 is 0. Here this is height is, balance factor of this is 1 minus 1 2. 1 minus 2 is minus 1. Minus 1. So here 0. So all balance factor is 0 minus 1 0 0 0. This is balanced one. Now after this, the same diagram only here given. Then after that we have a tree structure like this. Next element is a 6. We have to insert a 6. So after insert the 6, we have to insert 6. So we have taken the diagram 2 1 2 1 4 3 5 2 1 4 3 5. Balance factor is 0 0 0 0 minus 1. Now we have to insert a 6. Where to insert a 6? 6 is right hand side of this one, because 6 is compared to 2 which is greater, again compared to 4 which is greater, again compared to 5 which is greater, so 6 should come here. So after inserting this 6, we have to find the balance factor of all nodes. So 6 has the 0, because 0 minus 0 is 0. This is a leaf node, there is no height. And this, what is this value of this one? 1 minus 0 minus 1. 0 minus 1 is now balance factor, because there is no left hand side, only right height is a minus 1. What is this level? 1 minus 2, because this height of the left subtree is 1 and the height of the right subtree is 2. So it is minus 1. What is this new BF? This is new BFL. What is the height of this tree? The height of this tree node is BF of this node is 1 minus 1 2 3. So not this one. We can remove. This is 1 minus 1 2 3 is the longest path. 1 minus 2 equal to minus 2. So what happened? See here. This is 0. So here is also balance factor is 0 and 0. This is balance factor minus 1 is allowed, and minus 1 allowed, minus 1 0. But here is minus 2, it's not allowed. So what we have to do? We have to do a rotations. And before that we have to find what kind of imbalance is this. This is right imbalance. Right, because right hand side, right imbalance, right imbalance. And also where to rotate, because we have minus 2 is here, this node only, there is other remaining node have values minus 1. So only this root node has minus 2. We have to rotate this one, this lower this as a left rotation, because this is right skewed one, left rotation it required. So after left rotation, 2 will come here, 2 will come here, 1, then we have here values 4 will go here, and 5, 6. Then what about 3? Because 4 is as a root node. What about 3? 3 is the left child of this 4. So left child of this 4 means 3 will go move here and it go to its right child. Now check its balance factor. It is 0, 0. This is 0, and the 0 minus 1 is minus 1. This is a 0, and now it's a 1, 2, 1, 2 is a 0. So this is the factor here. So now the child, because this is a right child of this one, it has to go to its right hand side, but this right child of 2, it has to go to right child of 2. Next, now we have to insert a 7. Where to insert 7? After 6, because right hand side of 6. Now uh, we have to insert 7 here. 7. 7 is compared with 4, which is greater 5, and 6, which is come 7 will come here. Okay, so we have to insert it. Now what is the balance factor of this? Is this one is a 0, and what is the balance factor of this one? Now become its 0 minus 1 is now become its minus 1. Now what is the balance factor of this one? 0 minus 2. 0 minus 2 is minus 2 balance factor. And what is the balance factor of this one? 1, 2. Height is 1, 2 of the left subtree. Height of the right subtree 1, 2, 3. So 1, 2, 3 means 2 minus 3. 2 minus 3 equal to minus 1. And what is the balance factor of this node? Is 0. This node is 0. This is 0. So now df of this, all this node are minus 1, 0, but except this one, so this not allowed. So here we have it's a imbalance one. What imbalance is this? It's a left to left imbalance. See here, left, sorry, not left, left, right imbalance. It's right hand side, no? Right imbalance. If it is right imbalance, what rotation it requires? It requires RR. Right means right imbalance means what it requires? It requires left rotation. Left rotation. So only where we have to rotate it, because this node only has minus 2. Another node has value as minus 2, minus 1 or other value. This one. So we have to rotate this one. We have to rotate this one in the left hand side. If we rotate this one, what happens? 6 will go here, 5 will come. So 4, 2, 1, 3. Then 6 will go here, 5 come pull down, and 7 will come here. Now check this balance factor, all will become 0, 0. This is 0, this is 0, 0, and this is also 0. Now check it. Here 3 is it's an imbalanced one. So where it requires rotation means this node only has the minus 2 value. So here it, suppose you have 2 minus 2 here means, then we have to rotate in the lower level, then we check again. Okay, so this one it requires this 3 nodes only require these 3 nodes are imbalanced. That is, what is the imbalance? Right imbalance. So it requires left rotation. Now we have to insert 8. After inserting 8, where to insert 8? 8 is in the right hand side of 7. So we have a balance factor, this one. After inserting 8, we have balance factor of this 4 is 1, 2. 2 minus 1, 2, 3 is minus 1. So minus 1, 0, 0, 0, 0. So this is ABL tree. So ABL tree is a strictly balanced binary search tree. The node's balance factor should have 0, minus 1, or either 1. Next one, how to do search operation in ABL tree? ABL tree search operation is the same as a binary search tree, and we have to compare this each element one by one, and access the value. Deletion operations. Once you delete if you want to delete any element in ABL tree, we have to, after deletions, based on the BST deletion rule, based on the BST deletion rule, we have to delete the node. Then we have to rearrange the node, restructure the tree. So deletions operations we will discuss in next session. Thank you.